Hey, AP Calculus BC students, Mr. Record here, and we are going to spend a little bit of time in this video talking about one of the many tests to determine convergence or divergence of a series. And this video's test is called the limit comparison test. And I'm going to do a couple of examples that correspond to my notes for my Avon students, examples 3A and B. And I'm going to back up a slide or two here and formally introduce the limit comparison test as we discussed it in class. And it's actually a very clean, concise, easy to use test. We have just spent time talking about the direct comparison test at the beginning of this section. And what we have sort of find out from time to time is that often a series will closely resemble, let's say, a p-series or a geometric series, but it's a little tricky to establish the term-by-term comparison necessary to apply the direct comparison test. If you recall, in the direct comparison test, let's say that you've got an nth term expression that you're trying to figure out whether the series of this nth term expression converges or diverges. Well, what you have to do is you have to come up with your own nth term expression that I will call b sub n, and maybe that b sub n happens to be greater than or equal to the a sub n for a certain number of terms, or perhaps that b sub n is less than or equal to the a sub n. A lot of it just depends on what you're trying to establish with your direct comparison test. And in the case of my students, I use the analogy of the airplanes. Well, in the situation that we're confronted with here, this can be very tricky to determine sometimes. You know, which of those nth term expressions is truly larger, especially if they're full of some really strange symbols, like with the exponentials or factorials or whatnot. And you might have to plug in numbers for n, 1 and 2 and 3 and 4, and compare one at a time who exactly is bigger. And without the use of a calculator, that can get very, very tricky. So the limit comparison test sort of bypasses that step, and it just simply says, hey, go ahead and find some kind of a bn expression to use to compare your an with, but you don't have to worry about which one is bigger or smaller. So the limit comparison test, as it states in the Larson textbook, suppose you have a couple of series or a couple of nth term expressions, an and bn, that are positive. Well, what you could simply do is, if the an expression is the one that you're trying to find whether or not the series converges or diverges, just simply divide it by your made-up bn expression, take that limit as n approaches infinity, and you'll perhaps spit out an answer L. Well, if L is a finite and positive number, then what that means is that the two series will do the same thing. So it's vitally important that the series here that you've selected with the bn expression, the b sub n nth term expression, you have to know its behavior. You have to know whether it converges or diverges, and that will be pretty easy because you're the one who discovered that series. Okay? Going back, do your division, take the limit, and if your limit is finite and positive, now you got to be careful because things that are not finite and positive would be infinities or negative infinities. 0 is a bad result because that's not positive. And of course, any negative number, I'll call it the constant a, that would be bad, where a is a positive. Okay? Negative a would be a negative. So we want to avoid these things. If we do that, then we know that a sub n and b sub n as series do the same thing. Okay, well, that being said, you get a little bit of a helpful hint here. Let's say that your homework questions or test questions fall into this first column. You're trying to figure out the convergence or divergence of these three things. Well, what you're going to find out that you can do is strip away a lot of the excess. For this particular series here, this 5 down at the bottom really doesn't come into play. It doesn't really say a lot as far as the growth of this series. Likewise here with this 4n. It's the higher degreed exponent that's really determining where things are going in this denominator. And for that matter, this 3 has a very little effect. So you can see that if you strip away those things, what you've got is 1 over n squared. And this is a great thing to compare with, because you know that 1 over n squared as a series will converge. It's a convergent p series. So hopefully you can kind of see in the second example then how 1 over the square root of 3n minus 2 could really just be compared with 1 over the square root of n. And in the third one, once you strip away the 10, the n cubed, then the 4, n squared over n to the 5th really just becomes 1 over n cubed. And in this case, you also have a convergent series. The second one obviously is a divergent p series. But whatever the case is, once you can establish the relationship between the limit of one of these functions divided by the other, you're all set to go. And one last thing I wanted to suggest here, if we go back to the limit comparison test, do not get hung up on the order in which you divide, because it is not important. Let's say that you put your made-up series, Bn, on top of the original series, An. No harm's done, because L will still be the same kind of entity. For example, what if one way L turns out to be, say, 5? Say we had An on top, Bn on the bottom. Well, if those were flipped, then L would just simply be 1/5. In either case, we're finite and positive. Okay? So let's take on our first example here. 3a, we have square root of n over n squared. Well, obviously we can see that this 1 has very little effect on the problem, so we can essentially kind of get rid of him just for the time being. And then we see that the square root of n over n squared remains. So really what that is saying is that we can compare our an to our b sub n, which would be, well, the square root of n over n squared, but I think we could go ahead and simplify that just a little bit more. Subtract our exponents 1/2 minus 2, and we would have 1/2 or 3/2 that would be located in the denominator. And it is very important that we understand that this is convergent. Now, if you don't understand why that is convergent, you probably ought to take a look at P-series, either one of my videos or any of the many videos out on YouTube, to get more comfortable with that. But this is simply a convergent P-series, I'll say. So then we can jump all over our limit comparison test, which just says, all right, now let's make this a different color. Let's look at the limit as n approaches infinity of our original a sub n expression divided by our made up, our brand new bn with which we're going to compare an. Well, in order to take this limit, I think we would best be served by multiplying by the reciprocal. And I think I'm going to go ahead and change the square root of n to n to the 1/2 to make things a little easier. N to the 3/2 over 1 now presents itself. And if we do a little bit of algebra here and multiplying these numerators, n to the 1/2 times n to the 3/2 is going to be n squared, which gives us a fairly easy limit to evaluate. If you remember, whenever you are taking the limit of a rational function where n approaches infinity, you can then just compare the exponents, the degrees of the top and the bottom. Since they're both the same, we know that we can divide by the coefficients, and in doing so we get 1 over 1, which is 1, which quite obviously is finite. It's not infinity or negative infinity, and it's pretty certainly positive as well. So that means the criteria of the limit comparison test hold, and whatever our original Bn series does, right? The 1 over n to the 3/2 as n would go from 1 to infinity. Since we know that converges, then we also know that our original series converges. Now, unfortunately, you're not going to be able to determine what value this converges to. There's only a special select few genres of series that we're going to study where we can either find the sum exactly or get pretty close to the sum. But for right now, this would take care of it, answers the question. Now, let's take a look at one more example. I think it's down here. There he is, part B. And it's really the same kind of thing. It's asking you, hey, does this guy converge? Does this guy diverge? Well, we're going to have to really put our thinking caps on in trying to find something to compare this with. Well, let's see if we can start stripping some things away. Obviously, this one has very little effect on what's happening. But what we've got left may not be real appetizing. It might be really difficult to play around with. It might be very tough to see whether or not it converges or diverges. So if you just think about things a little bit, look at this numerator. What has the larger effect on the growth of this numerator? Is it the n, or is it the 2 to the n exponential? Think about how, as n gets bigger and bigger, what or which of these two pieces gets larger and larger? Well, obviously it's the 2 to the n. But I'm not going to say, hey, the n doesn't have any kind of significance, because what you could do with this is, rather than just get rid of the n altogether and leave, say, 4n cubed in the bottom, which I believe would work, we could just go ahead and cancel this n with one of those exponents. So this would now be a squared. Okay. Now I'm going to get rid of all this because I don't want to lose track of what the original series was. So to sort of summarize what I just spoke about, we'll just compare this with the series where we get rid of the 1 and do just a little bit of canceling with some powers of n. Now, we could also take a look at this and think, well, the 4 doesn't really have much of a bearing on the growth of this thing. You can't cancel the 2 and the 4. That's against the rules of algebra. But we could just sort of erase this 4 and say that really the comparison is going to work just as nicely with this guy. And I think we got a pretty easy function, or a pretty easy nth term expression here to play around with. The only question is, does this converge or diverge? What do you think? Because we have to know, otherwise there's no point in using it. Well, I would say just kind of rely on some of your techniques that you've learned probably prior to watching this video. One of the first techniques or tests for convergence or divergence was called the Nth Term Test. Now, the Nth Term Test is a little bit limiting in that it really only determines whether or not a series will diverge. But that's okay. Maybe that's what this thing does. So, divergence, I should say. So let's go ahead and, dive into the nth term test for divergence. So that would say we would take the limit as n approaches infinity of just this nth term expression. Well, this one's a little tougher than the last example because we do get an indeterminate form if we try to replace n with infinity, but that's okay because we know we can use something called L'Hopital's rule in this instance. So that means we will go ahead and we will take the derivative of the top, and that's a tricky derivative that you might need to review. You don't see that too often in calculus, in AP calculus at least. And then you take the derivative of the bottom, which is a little unfortunate because we still have an indeterminate form of infinity over infinity. But as you can see, we are making some headway with this denominator. We are slowly getting this guy to whittle down to perhaps not having some kind of a variable in it. So let's go ahead and take the derivative of the top again. This natural log of 2 is a constant that we'll just pull in front, and then we'll take the derivative of ln of 2 to the n, which gives us another natural log of 2 times 2 to the n. But lo and behold, now the denominator becomes 2, which means we do get a large infinity value on top and a constant on the bottom. And that's a wonderful thing when you're using the nth term test. Because remember, the nth term test for divergence says if you get anything out of this limit's answer besides 0, that means you diverge. If you were to get 0, it just means the nth term test is inconclusive. You might diverge still, but you might converge. So, all of that work just to establish the behavior of the series, or the nth term expression, b sub n, I'll call this, that we're going to use in our limit comparison test. So, let's switch colors here and jump right on our limit. We will take the limit as n approaches infinity. Once again, it doesn't make any difference who's on top. As a general rule, I typically will put the original problem in my homework or my quizzes or my test in the numerator. And then in the denominator, I'll put my 2 to the n over n squared. Now, to save a step, and I think you're all going to be okay with this, let's just multiply by the reciprocal. All right, I don't like to show that as, like, say, my first example or so, but since this is the second exposure to the limit comparison test, I'm sure that you all follow that we can just multiply by the reciprocal. And that's going to lead to a lot of really cool stuff happening, like these two guys canceling. Do not cancel the n squared and the n cubed. That would be illegal. But we can, as you can tell, multiply or consolidate the numerator. And that's a good thing because we have a limit that is very simple to solve. Okay, that's a good indication that you picked a pretty good guy right up here. You picked a really good nth term expression to use. This limit obviously would be 1/4. 1/4 is pretty finite, and it is pretty positive. So the behavior of our series that we were given should match the behavior of the series that we sort of made up, discovered on ourselves. So the answer would be diverge. And I'm not going to demonstrate this, but I do want to talk about this a little bit. If you wanted to check these answers and you had say a graphing calculator that had the summation capabilities, it would be pretty easy to verify this. I will warn you, though, you want to stay away from entering summations into your calculator where you do go the full distance. In other words, you probably don't want to enter this because it would probably sort of clock out your calculator, sometimes is what we call it, because it is just a too robust of a calculation. But instead, you can sort of cheat and maybe stop the upper index at, say, 100, and most calculators on the market now will compute that series pretty quickly. If you feel like you're getting a pretty large number, then there's a good chance that you're divergent. The only thing is, large is a pretty vague, ambiguous definition because what exactly means large. So sometimes I'll suggest to my students, go maybe up to 1,000 and see how much larger you're getting, and if it does seem to be relatively a significant jump in size, then it's a pretty good bet that you're diverging. Anyway, I hope this helps, and we'll see you next time.